we have already learned chapter 8. But in chapter 8, there is one important topic I did not have time to cover in class. So here I use this small video to explain this small topic. So what is the topic? Linear search versus binary search. We want to compare their performances. We know binary search is faster, but we may not have a lot of detail about how much faster. Okay, so here we want to see that problem. Okay, so we want to see how much faster for binary search comparing with linear search. So we want to, get a much better idea on it. So right now, our idea is not, our understanding for this topic is not very clear. Okay. All right. From the lecture notes, we have learned this result. For the linear search, the performance, the number of comparisons we need to use, we have a function approximately C times n. Here, n is the number of elements in the array, or we call it data size, and a C, some constant. Usually we do not specify it, but if we need, we can have it. So here for the binary search, remember, when we use the average case performance, this C equals 1/2. Okay? All right. The binary search, we have approximately C log n. Okay? C log n. Yeah. So comparing these two functions, we know log n is smaller than n when n is large, especially when n is large. All right. But how large is the difference? We do not have a clear idea. So we want to see it here. Okay. So we need to use some way that we can feel about it. So we can get some sense, concrete sense on it. Yeah. So that's the main thing we need to do here. All right. So look at this issue from data. So we need some numbers. We need to compare some concrete numbers so we can get a better idea. So let's do in this slide. Using some concrete data. So what kind of data we need? The first example, we use array size 1,000. So there are 1,000 elements in this array. Now, let's apply linear search, binary search on it, and see how many comparisons do we use for these two different methods. All right? Okay. Linear search, let's use average case. Okay? Yeah. Because that's the best one to describe the overall performance. So average case, 500. Okay? Because 1/2 of 1,000. So that's simple, 500. Okay? The formula n/2. Okay? Next, for the binary search, here we use the worst case. Okay? So you may ask me why we use worst case. So I'll explain to you. The worst case is log of 1,000. Log of 1,000. So this log here, we omit the base number because in computer science, we frequently use binary system, right? So the binary, so that corresponds to 2. So if we omit the base, we use that 2 as the default base. So that means it is log base 2 of 1,000. Right? Yeah. So we want to know this number. Yeah. Now let me explain a little bit why I use worst case here instead of average case. Actually, when we compare performance of two different methods, we'd better compare average case performance, because the average case is the best one to describe the overall performance. That's true. So that should be the same for the binary search. For binary search, the best one we use should be average case, right? All right, so here we know to calculate the average case performance for the binary search is much harder than calculate the worst case. The worst case is much easier to calculate, yeah. Because here in this class, so our CS 2250 in this class, programming and data structure, we do not do analysis on algorithms. It's out of our scope. So we cannot do analysis, or we cannot calculate the average case performance for the binary search. So too much math, okay? So I skip that. But I can tell you the result. The result is the average case performance is very close to the worst case performance. Very close. So how much close? Let me tell you. Within one, okay? Within one comparison, less than one, okay? So that means worst case minus average case, the difference is less than one. So although we use worst case here, but it's very close to the average case. So no problem. Yeah. The approximation is really good here. All right, so now let's move to find this number, log base 2 of 1,000. Here we want to estimate it. Yeah. Although you can use a calculator, so you can find the number immediately. Yeah, but here, you know, we do not need a precise number. We just need a, you know, approximate number. Yeah. And if you do not have the calculator, so then we can figure out easily like this. Okay. We start here. You should know this simple fact. 2 to the 10th power equals 1,024. Do you know this? You should know this. Okay. Why? Because it corresponds to the kilobyte. So what is the kilobyte? 1 kilobyte equals 1,024 bytes. How that number, you know, comes from this 2 to the 10th power. Okay? So we use that. Then we can use 1,024 to approximate 1,000. They're very close. So we just, you know, drop that remainder 24. Okay? Yeah. So, you know, now it is a, you know, pretty good approximation for us. Okay? 2 to the 10th approximately equal to 1,000. So if we take a log base 2, so we get this. Log base 2 of 1,000 approximately equal to 10. That's a good number. Okay? So let's use it for comparison. Okay? So now we compare these two numbers, 510. Okay? So the ratio, 500 over 10, that's 50. Okay? Is that big? Right? So, you know, that's pretty big. But next, we want to see, you know, more evidence. So we want to see stronger evidence. So we move to next size. Our next size is much bigger. That's 1 million. Okay? So that means we have an array with 1 million elements. Now we want to apply linear search and a binary search and see how many comparisons do they need for each case. Okay? All right. So linear search, that's easy. Approximately 1/2. So that's 500,000. Binary search, log base 2 of 1 million. What's that number? We need to figure out. Okay? Yeah, I mean, just use the previous method, but we need to modify it a little bit, all right? So let's do, make this observation. 2 to the 10th times 2 to the 10th approximately equal to 1,000 times 1,000. So that's 1 million, all right? So let's simplify it. 2 to the 20th approximately equal to 1 million, right? So if you can see it, then we take log base 2, both sides. So we make log base 2 of 1 million approximately equal to 20. See? Here, we only need 20 comparisons. We can use binary search to find the element in that array. Oh, here, let me make one big important clarification. Because if we apply binary search, linear search, both on the same array, this array must be sorted. Otherwise, we cannot apply binary search, right? So one thing to be clear, this array must be sorted. Okay, let's assume in ascending order. Otherwise, it does not make sense. Okay, otherwise we can only use linear search. We cannot use binary search. Okay, yeah. So make that clear. Then we make this comparison. All right. Now we can see the big difference. This time the ratio is 25,000. That's really big. Okay, 25,000. That's really big difference. Okay, so you get a clear idea. All right, but this is just 1 million elements. Can you imagine if you have 1 billion elements? This ratio is even much greater. Okay, so now I think everybody can see how big difference between these two methods. All right. Okay. So for this small topic, I just want to stop here. All right.